We're delighted here today to be able to talk about something that's been a great source of excitement to many people. A couple years ago, I didn't know very many of you, and now I would call many of you friends. We've spent so much time talking and interacting about some of the content that's here, and we're really delighted to share that more broadly. I'm CJ Newbern, and people ask me what my job is, and it's something like troublemaker. I try to look a year or two ahead inside of a product group and figure out what kinds of things should we be working on to solve tomorrow's problems, to sort of meet the puck where it's going. And I'm delighted to, one of the areas that I've spent a lot of time and seen a lot of opportunity for is in storage. So I've worked in data center architecture, security, lots of other areas. I'm really delighted to be working with my mentor of over 30 years, Wenmei Hu, who's going to be co-presenting. And he sort of drives all of our storage efforts inside NVIDIA Research. So today we're going to talk about a number of the storage implications for a new generation of applications. And I just have, it's been amazing to me. I've never seen software move so fast as it has been in even the last year. Was at a staff meeting a while back, and somebody asked sort of the latest on what was going with KV cache. And my answer was like, well, here's what it is, but all I know for certain is that it's going to be different in 3 weeks because it's moving so fast. So whatever you think you knew, maybe you'll leave this room thinking something different. And we're going to lay out our views of a number of things, but we really encourage this to be a long-term interaction where we're hearing from you about your perspectives, because we really passionate about being data-driven. So kind of the place that we're going to start with this is just looking at, if you look at storage in general, what are the different parameters that you care about? We'll talk about a couple up front that aren't particularly tied to applications, and then we'll move into a number that are really driven by the applications, which Wenmei is going to walk us through. So one of the things that really hasn't been much of a consideration is, we think of trying to essentially we got some more seats up here if you want to come along, or you can come along the sides, whatever. We think of storage as either being a couple disks inside of a compute node or being someplace far away. And there's actually a middle ground. And each of them has a different purpose. Each of them is optimized for different things and so on. And we are going to have sent these slides, but we sent them late, so they're not yet posted. So some of the things that are close by, when you really need minimal latency, you can put them there. In places that are far away, you may be able to sort of get to the shared bandwidth and IOPs for lots of GPUs, and you're looking at TCO considerations. There may be a new middle ground of something you could call cluster local storage, because you just can't fit all the capacity that you need for a KV cache, for example, in the compute node local, and you can't get enough IOPs. And maybe in some cases like data analytics, you can't get enough bandwidth. It may be managed. You can minimize the various different kinds of overhead with the RDMA, and they may be less contended. So we're going to look basically across different applications and see where those sit. One of the things that NVIDIA has been very reticent to do is to encourage people to go for a converged network and to kind of carefully separate, hey, the rightful place of storage is out of the back 40. I'm an IO boy, right? So way down yonder in the pawpaw patch, if you will. Well, they don't have pawpaw in Iowa, but for some reason we talked about that as a kid. Really you can't go any faster than whatever the speed of your CPU, and if that's have to go through that to get to your network, that's going to be your limiting factor. For the legacy storage, for the infrastructure control plane and so on, that's the place you want to go. And the NVs that are hanging off the CPU are going to be limited today until those catch up. But we're seeing that the GPUs are the places that, because they need to go over the network, have a really fast, sometimes 2x faster network connection to get to other memory, to get to other storage. And so that's where the focus is. And so if that's the place that you want to get to the faster storage, that may be a better place to put it. And if storage now begins to be an extension of memory of, instead of having compute nodes talk to each other to share memory, they're just sharing memory that just happens to be stored in NAND, then maybe that's a place to put it. So that's something we can look at. And just as a quick illustration, in a GP300 node, I had to get permission to do this. I had to find out, make sure that somebody else had done this before. This shows where we have a CX8 connection over Gen 6 to be able to get out there. And so that path that's going east-west is sort of 2x of whatever you would be able to do if you went through the Gen 6 Grace CPU. And we're using CX7. So what are some of the different interfaces to storage? So there's kind of this workflow that you might think of where, who decides what it is that you're going to get? Who decides what that remote access is going to be, or the whatever the memory access is going to be? And then who decides when you're ready to do it? And how do you clean up afterwards? So it seems like it turns out that the CPU, which is where traditionally we've been initiating OLAIO, is meant and tailored for dealing with a limited amount of concurrency on the order of 100 threads. And yeah, you can make things short-circuited and get a little bit faster path by having the GPU say, hey, I'm done with this kernel, to be able to signal something that's right in a GPU queue that doesn't have to go all the way up and talk to the CPU, that uses that GPU hardware and triggers something right away. But if you now have 100,000 threads worth of concurrency, there's just no way that you can go back and talk to the CPU and get its help. You have to do it yourself. That leads us in a very different direction. So we're still good enough for a long time to come, have lots of applications that need and have only a limited amount of concurrency. CPUs are great for that. CPUs can initiate that. We have things like cuFile and cuObject as part of CUDA. And has anybody heard of S3, maybe S3 over RDMA? Like, nobody's been talking about that, right? Like, I don't know, if you haven't, maybe you should get out more. So then there's the notion of GPU initiated, where you may be able to get to data that's in storage, but it's probably going to be blocked because you don't want to stick a file system on there. And we have a couple different APIs for that in something new we call SCADA, one for contiguous linear and another that's working forward with some of our partners who happen to be sitting in a row over there for key value. So we have a number of different abstractions that are built on top of this. As part of Rapid's cuGraph, we have whole graph, which is really good for holding the embedding data in the graph neural network. And John Mazik gave a great talk on this. QVS, which is for vector search and vector indexing. We have something that's kind of taken off as part of Dynamo. One of the people that worked for when made Vikram has done a lot of work in coacting Dynamo, which helps with inference engines. And then, of course, the QData frames. And so these all map on top of CPUs and GPUs respectively and go to different kinds of underlying storage. So kind of just a key differentiator between these. There are a number of things. If you're doing something that's predictable, that you're doing fairly large pages with just a few threads and in large I/O sizes, and maybe you can prefetch something, then do the CPU-initiated thing. If what you need to do is something that's compute-driven, where you don't know what you're going to do ahead of time, and you really want to do it much more dynamically and in a fine-grained way where you can keep 100,000 threads busy figuring out what it is that they're going to do, then if they're fine enough, it's very convenient because you're still just saturating the PCIe. And now the challenge is, how do you feed that fast enough from storage? And a good thing, because there's some latency involved, the GPUs are actually better than CPUs at being able to tolerate the latency with this SIMT architecture and being able to buffer the data in HBM. So essentially you have several problems here, and as you might guess, this spells out SCADA. So the first is that it's scaled, so that you're talking about moving from the problem of only 100 threads to 100,000 threads. When I'll talk about the challenges related to partitioning. And you could try to do this over memory fabric, but it looks to us as though that tends to break at scale. So you really, load store isn't going to cut it for you. If you get a bus error, then you're dead. So, but if you have an API, then you can, lots of AI too. You can recover for that and support being able to have errors. It's accelerated because you can do this GPU-initiated thing we just talked about. You can't normally read directly into registers from I/O, so you can introduce a cache on the GPU for this. And you can get better at tolerating latency with GPUs. You can do aggregation, and we'll spend some time talking about that. And the key thing is to be able to do something you just couldn't do before, which is to be able to access an unbounded amount of storage, right? Unbounded amount of capacity. If you've got the money to be able to buy several racks full of GPUs just for the sake of HBM so that you can do everything in load store, knock yourself out. We're happy to sell those to you, but you may want to consider something else. And the key thing that we'll talk more about too is this notion of access of we've been bringing in big chunks and then in memory doing sparse random access to those, but that doesn't work if you're only going to access 2% of 2 petabytes. You want something that's much more dynamically be able to do that. So now I'm going to turn it over to Wenmei, who's going to walk us through a number of things related to apps.
Thanks, CJ. And when we look at the applications, we have these kind of a few branches. One is if it's very compute intensive, and you occasionally need some to access data. And that's where the traditional like LLM training and so on is. Then we have good infrastructure for that. Right now, we don't need to worry too much about it. And whenever there's a data-intensive application, then it depends. Right. So we can have some of the CPU-initiated prefetch as long as we know what the GPU threads are going to need. But when it comes to data-intensive applications, and we're going to talk about a few of those, such as vector search, such as graph analytics, and predictive AI based on graph relational databases, that's where we need to have the new infrastructure and most likely new hardware infrastructure from the SSDs and so on. So there are really two styles of the interactions between the compute node and the storage. So again, when it's compute intensive, then we have the traditional way of using the software stacks and the hardware infrastructure. From SSD's point of view, these SSDs can be fairly optimized for bandwidth. But whenever we start to get into these data-intensive and finer grain access applications, we start to have different. We needed to build that software stack, and this SCADA software stack has been in the work for almost 10 years. But this is the year that some of our partners are beginning to receive the code, and then we have the these fine-grained. The front end for software front end so that we can aggregate data enough, the request enough so that the existing hardware infrastructure, such as the NICs, such as the switches, such as the SSDs, can handle the level of IOPs we need rather than being the bottleneck. And then we can have the NAND. We're talking to many of the partners about the improvement, the future improvements in the median, so that we can achieve the IOPs that we need. So there are a few trends that we're talking about here. One is that data reach. So today, if you look at rack, many people will tell you that the racks are not that big. And the reason why the racks are not that big is because, one, we don't have nearly as many documents as we need in the rack. And then people are, this is kind of a self-fulfilling prophecy. We don't have the infrastructure to do it right, so people use small number of documents, and the documents are not chunked to the level that would be much more usable and accurate in the search. So we're beginning to see that the trend is going from 10 terabytes to about 1 petabyte. And so the throughput and concurrency, as CJ was saying, we're looking at a lot of these applications that previously used hundreds of threads on the CPU to now 100,000 threads on the GPU. For example, for graph neural network sampling, people used to do it on the CPU, But then about a year ago, most of the frameworks moved the sampling to the GPU. And that's exactly where we see that transition. And then the access pattern. We are looking at very sparse random accesses to Spark data. When you have a rack that is out of 1 million documents, and each document is broken into thousands and thousands of pieces, you're not going to be accessing more than a very small percentage of the data. So that's where the sparse access happened. And and programming model, the GPU, are becoming more and more autonomous. And we're beginning to see, for example, a few years ago, if we look at the frameworks for neural networks and so on, a lot of the activities, data loaders and so on, they're all very, very CPU centric. And then you occasionally go out to the GPU for the kind of the big chunky compute. But then now we're beginning to see that the GPU is actually doing almost the entire workflow, and it's very hard to break from the workflow out to ask for service and come back. And that's a very, very expensive process. So, CJ already alluded to that. So on the left, we have the today and sort of the yesterday and today. And these things are not going away. When we say yesterday, we didn't mean that they're gone. We mean that yesterday, these are the challenges that that we're working very hard to address. And these challenges are now the mainstream. But when we look ahead and we ask ourselves, what are the big challenges and where are the new markets, where are the data center new purchases and so on will be, and this is where we're looking at. For example, the model training and so on will be still there, the model parameters and so on. But we're going, and KV cache is very hot today, and they're going to be there tomorrow. But what we're looking at is that, how about databases? The whole database, the community is moving from the relational database to graph relational database. And so these are the kind of transitions we see will be where the big demands will be tomorrow. And we can do a few comparisons. We have too many slides, and we put all that information here for your reference after the talk. So I'm going to just kind of cover the most important points. The most important points is that for generation point of view, today we have text generation, we have image generation, we have all kinds of code generation, and all these things are based on very big context and very big embeddings and so on, and the information that we generate are mostly from the model. Okay, so and we do very, very little I/O or storage access through that whole process. But when we look forward, when we look at prediction, I'm going to go into one of the examples in detail. The need for data access versus compute is actually changed very significantly. And we're going to see knowledge graphs, we're going to see graph relational databases, we're going to see all kinds of things that are hard to partition, hard to pre-plan in terms of how you can supply the data to the compute. So and these things are growing, and on the left-hand side, we're seeing that for what we used to call the DLRM, the deep learning recommender systems. Basically, when Facebook and so on need to do this recommendation, they need to have all their users, somehow in a data structure and search for the recommendation and search for the let's say predicted link into the future connections and so on, and that's where the memory growth is. And for the vector databases, we have a similar situation. All these, the vector databases are growing, and as we work into the relational databases, these things are getting into petabyte and even exabyte, in terms of the corporate databases and so on. So again, this is we already went through this, this whole hierarchy, but what we're seeing on the right-hand side there, that's where the corner where we believe the IOPs per TCO is going to be the most important, and that's where we believe the next generation of media and design and the next generation of controller design will have the greatest impact. So what are the applications? One is this vector search pipeline. The vector search pipeline is extremely simple. This is conceptually as simple as it gets. You have these multiple media the representations, and you go through the data prep. And data prep is a fancy word. Basically, you chop things up a little bit. So images, you chop into smaller images so that you can use small chunks of the images for your inference, for example. And then you go feed that into the embedding model. So the embedding model is usually trained. And then so you generate the vector representation of a huge number of these documents and then images and so on. That's your vector, that's the vector database that you're going to use for retrieval augmented generation, for example. And then during the inference, when we do RAG, we will have the query come in from the right, just as usual. And then you will generate the embedding for the query, and then all the context and so on. And so the same embedding will be used to access the vector database to find any additional information, any additional embedding and so on you want to add into the context to either expand, because some of the users are very terse, so you want to be able to expand the query to include some of the information that the user implicitly talked about, right, in the query. And also in situations where you may have some of the models may be trained with certain types of document, but some of the documents are too new, so that if you have these new documents in the in the vector database, so that means that you need to update your vector database very frequently. Then you can put them into the context, and then that will give users the right kind of response. So there's three types of vector databases, and I'm not going to go into the details here, but just keep in mind that there's an online search use of vector database, and there's an offline search use of vector database. And these two have different latency constraints and different throughput, kind of emphasis. So after we look at the storage for long enough, we believe that even in the online search, we can meet all the deadlines. And obviously, the SS even in the current generation, but there are ways that we can reduce the system level cost and further reduce some of the latencies if we have the right kind of devices. And the index build is really the part that creates that whole database. And so I'm going to kind of quickly go into one of them. If you're interested in this area, there is an open source software infrastructure called QVS. And this QVS is being used by most of the vector databases when they port their vector database on the GPU today. And so when we index the vector database, the mental model for this is that you create a whole bunch of these chunks, and you generate the embedding vectors for these chunks. The embedding vectors are quite big. The embedding vectors need to be big enough to capture all the dimensionalities of the semantic information. So that's where the big need for space is. And then, if you generate embedding from scratch, you can afford to go through all the vectors. Basically, you're going to be looking at how to when something comes in, let's say a query comes in, you want to be able to take the embedding of the query and find all the vectors that are close enough to that embedding vector, right? It's a very classic HPC, nearest neighbor search problem, right? But here, we're beginning to use that in a very large scale for databases. So when we create these data embeddings, we're really creating basically nearest neighbor representations of a large number of items. So when we create that for from scratch, we're going to go through, we're going to read all the items in the database, and then we're going to generate those linkages, right? And those linkages need to be written to the storage because these linkages are really big. And you can think about the number of items times maybe K, for something like a KNN, we're going to talk about 32 to 64 neighbors to start. And then the bigger graphs will have even more number of nearest neighbors to represent. And that gives you the size of the graphs. So there are three types of ways to build the indices. And the first one is the most popular in the CPU world, called the log structure merge. And this is really just, in the old days, because we're trying to avoid writing frequently to the disk. So what we do is that every time we generate a whole bunch of new linkages, we group them together, call it a chunk, and write it into the disk. Unfortunately, when you search, this thing is very slow because you have all these generations of updates in the disk, and you need to follow the chain, and through the tree, eventually you will find the newest item that you want, and then you stop. Otherwise, you need to go all the way down to the chain for very, very old items. The one that a lot of people prefer today is the dynamic index or tier index, and this is the things like the small world graph and the K nearest neighbor graphs and so on. And so these are the graphs that have the best search performance. But then when you build these graphs, you really need to have, today you need to have the graphs to fit into the DRAM. And if you don't fit into the DRAM, what people do is that they cut up the data sets and generate the nearest graphs for each shard. Unfortunately, it's very hard to combine the index for those shards. So if you need to search, you need to look into all the shards. That's the unfortunate part. And then there's a global index, but I'm not going to go into that for time constraint. So I'm going to just talk about kgraph here. kgraph is a open source infrastructure code for people to build nearest neighbor graphs. And so the workflow is very, very simple. This is one of the simplest ways to build a KNN graph. By the way, all these are heuristics, so there's no perfect algorithm, okay? And so there's probably, there's still a lot of work that people need to do at scale. So we first built the initial KNN graph. Usually we would, if you want to eventually K end up being 32, you would probably build a graph with K equal to something like 96. And then you start to look at all the edges in that graph and say, oh, do I really need this edge? Because I could go up a little bit and come down a little bit. So this edge really doesn't have to be there. There's a detour for that edge. And I'll find whatever I need to find anyway. So you start to cut down all those kind of detourable edges from your graph. And that's the pruned graph. And you sort the pruned graph in terms of importance because you already evaluated the detourability. So you say, okay, all the detourable edges will go to the end. And then you generate reverse graph. And this is actually a very memory intensive process. You reverse the graph, and then you replace some of the edges in the original graph with the reverse graph edges. It's graph theoretically provable that this gives you more reachable nodes in the graph. And then you merge the two and you write it into the disk. Today, KGraph could not handle the generation of KN graph that requires more than the host memory. It just, currently, it just doesn't do it. So what happens is people generate multiple shards and multiple indices, and then when you search, you need to look at all of them. So the most memory-intensive part is the middle part, and this is what we use, SCADA today to extend the memory. And that's exactly one of the applications we're co-building SCADA with the vector search community. The second one is, I want to just say a few words about the GNN's, the whole graph, domain. So there is the graph, from NVIDIA's point of view, we have cuGraph, we have whole graph, but then there are also multiple graph packages. And the interesting part of graph is that the graph data is big, but it's much, much bigger when you start to consider embeddings. So thank God for embeddings. With embeddings, all the data structure are becoming so big, and this community is becoming so important. Without embeddings, we will probably be just having some beer and talk to each other about yesterday or something in these conferences. With embedding, we start to have 1,000 times bigger data in so many ways, so that it makes life so much more interesting. And these embeddings need to be sampled. These embeddings need to be found through graphs, and that gives you the random accesses. So, for example, when we train a neural network, to train a graph neural network, every time we get a training node, we will need to sample the neighbor, and we need to collect the embeddings of that neighbor. We may need to collect the neighbors of the neighbors. So there are up to 3 layers of sampling in most of the applications. And so that gives us the I/O, the batch size. So in this particular case, 5, 10, 15 is a very common the graph neural network sampling the 3 levels, 5 neighbors in one, 10 more neighbors in the second layer, and then 15 neighbors in the third layer. That gives us, with 1,024 training nodes, we will have 750K accesses. All these accesses need to be served by the SSDs or by our cache. So this is what CJ was referring to, right? We have a GPU-based sampling algorithm, and that sampling algorithm is going to generate the sampling list, which is 1,024 here. And then the 1,024 will be batched into and then the graph structure will be traversed by all the GPU threads, right? And the GPU threads will identify all the nodes of the neighbors and the neighbors' neighbors and so on. That's all part of the compute. And we have an aggregation approach in SCADA to be able to collect all these things into what we call the sampling tensor, and that gets shipped to the storage. So you will be for these kind of applications, you can be seeing thousands and thousands of requests in one shot because the GPU threads already did that work for you. We already collected everything, put them into a nice batch, and send it to you. That's why we're looking at some of the protocol changes and so on to make your life a lot easier. A few things that people are doing with with graph neural networks today. Based on the first principle, the LLMs are becoming bigger and bigger because you need to have all that context, and then you also need to have n-square approach to do the attention. So this is exactly the KQV is about in the LLM. But if you look at the graphs, a lot of these relationships are already encoded in an efficient way in the graphs. Whatever you need to pay attention to in the LLM is already marked explicitly in the graph, in these knowledge graphs. So that's why when you combine these two, if you use the graphs to give you some of the context, those contexts come with attention already. So you can actually be a lot more efficient that way. The trick is that the LLM embedding and the GNN embedding have to be compatible with each other, because in the end, you need to generate based on LLM. So that's why the graph retrieval need to be jointly encoded with the LLM to generate the embedding to be able to function correctly. And so one of the important deficiencies that we currently have is most of the knowledge graphs are not big enough. However, there are recent research that enable the LLMs to generate the knowledge graph. And why do you bother to do this? The reason is once you generate into the knowledge graph, next time when you use it for the GNN, you can actually be a lot more efficient, right? So it's almost like we memorize some of the things in in math. We don't need to always do the calculation. A lot of the things we already remember in our head, right? So that's exactly what it is. One last thing about the
graph is what we call the graph relational database. And this actually took me a little while to appreciate, when after CJ initially brought it up. So we have relational databases, and we have the rows and columns, right? So in a graph relational database, we assume that there are multiple tables, and these tables have, these tables would, for example, for an e-commerce site, you will have all the users in one table, big table, and you have all the products, right, in a table, another big table, sales, which is even bigger because you have all the transactions and so on, right? And these tables have natural information that link to each other because a sale record will have a user ID, will have a product ID, and so on. So what happens is people are now beginning to build explicit graphs because using IDs to look for things during the inference is a slow process. So people start to build these huge graphs that actually give you instant access of the related information from the relational databases. And then you you can train a graph transformer based on these things. For example, you can say, let me train a fraud detection, the graph transformer. So what happens is, for each transaction that is fraud in the past, you find all the neighbors of that node and you train a graph transformer. And in the future, when you see something like this, you will be able to detect the fraud right away. Okay, CJ.
Thanks very much, Wenmei. So we're going to talk about a variety of these different storage parameters now that Wenmei has set them up. So one of the things that I'm going to start about with is criticality. So actually, I'm going to do a quiz here just for fun. So how many people think that for checkpointing that performance is critical at the compute node? Wow, nobody took the bait. Oh, there we got one. Yeah, got you on the ML perf. That's right. I got some good data from last. Okay, how many people think that the majority of cases with KB cache have a sensitivity to latency? Okay, a few more hands. And how many people think that the majority of cases for KB cache are sensitive also to bandwidth at the compute node? Okay, all right, some more. All right, great. So let's look at that some. So essentially, the thing that really matters is between the data-centric and compute-centric, this sort of drives and is driven by the I/O to compute ratio. So some things that have a fairly low ratio of I/O to compute are LLM training. Spend lots of time, lots of GPUs doing a bunch of training, but not that much I/O, relatively speaking. They still do a lot of I/O. Usually low, for most cases, is the LLM inference. And there are cases in model load, but even in model load, it's critical when you want to spin up a new worker, but it's kind of a trick question because it was critical enough that people decided to keep them in memory all the time and use enough GPUs to be able to keep those in memory. And so the actual time as you switch experts to sort of load in the new data doesn't end up happening that often. So let's look at some other, whereas some things that are high are this search for predictive AI or vector database indexing. And some examples for where the size of transfer matters. An example is if you have 100 megabyte PDF files that you're gonna go and pepper with a bunch of questions, that's a lot of context. And so that's something that you're gonna need to get in a hurry as soon as you figure out you're starting to ask questions about that. That's pretty invasive to your system. But if rather your new context is something like tens or even 100,000, your input, your ISL has lots of tokens, or you're going to be producing lots of output, or you need so many compute elements that you're going to be drawing all that data in through lots of NICs and lots of GPUs anyway before it gets to its final destination, it may not in fact be that critical. Another case is that y'all didn't take my bait with checkpointing is that a lot of us have gotten excited saying, this is the answer, but actually checkpointing really does matter in the back-end storage because you have so many GPUs that you're trying to support. On the compute side, if you take the model parameter space that you have and you spread it out across 100,000 GPUs, then the amount that you need to store per GPU is tiny. It'll matter, it could matter, you thought it mattered in that case because you're gonna fail so often, but if you have a small system, then you're gonna fail, every couple weeks or at least hours, so it doesn't really matter, right, and it goes away. One of the other key metrics that you use for time to first token, you wanna look carefully with respect to human perception because humans can't tell the difference if it's between like 100 and 250 milliseconds. And so if you're doing something a little bit faster, but the faster basically stays within that amount, then it kind of doesn't really matter. And a lot of the agentic stuff, you have to get your entire answer before you go on to the next stage anyway, and so that latency doesn't matter. In a lot of cases, it's the overall throughput that does. So summary of capacity. This training data, there's a lot of it, and there can be a huge amount of context in the KV cache. Model parameters, there's some figures here, but this vector database and indexes, these can get up to a petabyte per worker, and GNNs can also get especially large. We're starting to have some conversation with retailers in e-commerce, for example, that are trying to look at being able to help shoppers figure out what they want to buy every time they go online. So you can also ask a key question of, so now I want to be able to do all of these fine-grained accesses, and I need to be able to do this to disk if my problem is too big to fit. If I just have one disk, that's nice because I can now work on a bigger problem. If I want to get the full performance, I might need lots of disks. So where am I going to put all those disks? If you do a little math and you look at, for the PCIe generation, if you're doing 512-byte IOPs, that number of IOPs gets huge. And even if you get lots and lots of drives, I just totally made up some numbers as to sort of how many it might take. That's still way too many drives per GPU to ever fit in a compute node. Forget it. Right? That doesn't mean that it isn't useful to have fewer drives. It just means if you want to get full performance that's totally unconstrained by the number of drives, that gets a little crazy. And that changes your storage architecture. If you remember me talking about that sort of compute local storage or cluster local storage, you may want to have it at the top of the rack. And if that's 5 microseconds to get there, that's not so much of a problem. So let's look at breaking the problem down as to what are the key things we need to solve. One is you got these GPUs. They're creating all of these this demand for IOPs, and they can create big buffers full of requests and ship them out. If you were to ship them out there's a request, there's a request, there's a request. The NICs just can't keep up. But if you take big batches of them, then you can use the NIC to its full standard bandwidth because you're actually making large transactions, okay? And we did some characterization of like, what could you do with IB write bandwidth? And there's something in the data center on a chip, the Doka GPU net IO. You can be pretty efficient with respect to that. And we're reasonably efficient, and that number is coming up as we go. So the next thing is, So now, especially if I'm going to bring things back as responses, as data responses and acknowledgements, I'm going to be doing RDMA. There's some fun discussion this week about RDMAs. So how do those keep up, especially if those are little teeny tiny things? And the concern is that if you're moving something that's really small, but you have a bunch of packet overhead, that can sort of drown out some of the benefit. And that can, we sort of characterized what the effective packet header size was with Ethernet, and it looked like it was about 98. And it's 64 bytes for just an acknowledgement. That's sort of like an efficiency loss of 35%. So you can do okay with Ethernet, but IB may be better. That's just something to consider. So the next question is how, when we're doing the other part, where we have made the requests and out towards the storage and we're trying to get those back, now you have sort of not only the request, but you have a data response, maybe that's 512 bytes, and you have an RDMA notification, maybe that's 64 bytes. Those can essentially drown you with all this little teeny tiny inefficient traffic, right? We can't bundle those things together unless we pack them on one side, ship them to the other, and sort of unpack them on the other side, which adds a little bit of latency, takes some more compute. Could do that, but we found ways that we could basically bundle these and get a 1.4 increase in the effective IOPs and bandwidth by essentially coalescing data requests that were had similar data and similar flags. And so that looks promising, and that looks like something that we may want to look more carefully at on the performance side. We've done some characterization, didn't quite get this on Gen 6 data, but for Gen 5, we're basically maxing out with an H100 what the performance at the IOPS that you can get with a whole mess of drives and a special box. We did this with H3, thank you very much. And we found that Gen 4 GPUs, about half of that, but a Gen 5 CPU was only getting about half, less than half, of what a Gen 5 GPU was. The CPU was panting and running out of breath at full utilization, and the GPU is barely breaking a sweat at about 25% occupancy. So a lot more headroom there on the GPU to be able to do a lot more processing. And this was just measuring the requests being handed off to the drives. This is the slide that I'm most excited about here. So we did some end-to-end work. So our first application with SCADA has been looking at whole graph. So this is taking the GNN work that Wenmei was talking about. And how many of you sort of like, if you would think about it in your head of how much slower do I think it would be to go to drives as opposed to going to memory? And this result said that if you compare that, if you had the GPU, if you're going to have GPU going to its own HBM, that's screaming. That's like 10x faster than if you were going to the CPU memory. But if now to going to disk, instead of going to CPU memory, this result showed that we were basically 1.2x slower. So you're getting basically an unbounded amount of space. So if this is sort of, you're increasing your embedding size, you go up into the point with GPU memory, that's the top line, until sort of like on a given node you can't hold anymore. In the yellow line for CPU, you get to go farther to like a terabyte or two. And basically the green can keep going. And the interesting thing is, as there's a little uptick of where that gap actually narrows as you get to bigger sizes because you're presenting more concurrency. The fundamental thing that GPUs are really good at is if your application really has lots of concurrency, you can hand that to it and really scream. So what are the performance takeaways from this? So the IOPS are of sort of to unlimited data size is approaching access to the CPU over the PCIe. That's just never happened before. And that fundamentally changes what kinds of problems you can work on. So your mileage is going to vary. I was kind of terrified to share that 1.2x number because like everyone's going to like, oh, I can get everything on every app with 1.2. It's like, no, don't think so. It's too early to make any such claim. I'd be horribly irresponsible, so please don't misquote me as doing that. But this is real data, and we think that we have a bunch of obvious headroom that we see to be able to improve that. The key thing we want to dig into is the access patterns and how workloads access patterns map onto what it is that you can actually squirt out to a drive and how efficiently we can make that work, especially over the network. What I showed you before is just basically inside the same box. So we have a variety of different access patterns. I'm running tight enough time, I'm not going to be able to work through these, but I'll leave these on the slide. And we're showing that basically decoupling from the standard way of using MD-span and reading things into memory, if you can basically go and say, I can have every thread just queue up a whole bunch of misses and then have those be serviced back to memory and then read them out in bulk, that's going to be faster. But that may take a little more work. But it doesn't mean if the application already exposed all the concurrency, you should be able to harvest that, we hope, without an excess of effort. It doesn't mean restructuring your application. It means sort of tweaking the particulars of your access patterns. That's our belief, but we have to prove that. So we really need your help to sort of work with applications and see the degree to which that's true. And so there's a lot of work ahead of us sort of mapping apps to those cases and evaluating the performance. I'm going to skip looking at latency, but there's an analysis here of where latency does and doesn't matter. I'm going to note that there's a lot of been discussion of S3 over RDMA, and we're seeing that when you use RDMA instead of TCP, that you can get like 3x of throughput and 3x better latency and 20 to even 50x better CPU load. And there are a lot of opportunities for that. We sort of combined that with a QVS that was giving us 5x and got another 1.6x using S3 over RDMA in Cloudine's case to be able to bring that in for a total gain of being able to get 8x with that. Kind of excited about that. And so how do you want to jump into this 1 minute here? Okay. So the fundamental thing that we have essentially is that we believe that the key thing we want to do is not just to be able to bring data into chunks, but to be able to directly access data that is on storage. That's only feasible if you can do it, and if you can, which you haven't been able to do to date, and you can do that with reasonable performance overhead. We are frankly shooting for an order of magnitude slower, and we're exceeding our targets with this. We're doing this with an abstraction called SCADA, which I mentioned here is sort of the, oops, there we go, wrong way. The scaled accelerated data access. We have a lot of work that we're doing in the ecosystem to sort of make that work. Dealing with, we don't today aren't able to ingest data from the disk, be able to operate it and spit it back out to the file system. But that's a key, that interoperability is a key thing we're looking at doing, and adding in data integrity and key value store for this. An effort that we have driving this is Storage Next, which is to define and refine these IOPs per TCO optimized SSDs. We're amazing response for companies represented in the room in this space. That effort is really to evaluate and optimize and generalize this. It's a joint exploration. We're trying to mature the technology until it's ready to be standardized and trying to move that forward. We're basically looking for people that have some skin in the game across a variety of different areas. And we're looking forward to the point where that's mature enough that we can bring it out sort of to the public for standardization. There are a number of companies that are we've delighted to have as part of this. And so our ask is to understand these implications for the different kinds of applications, look at what's critical and look at some of these different examples, bring us your applications and frameworks and evaluate those. We're developing some technology for being able to do tracing and analysis. We really see this as a hardware-software co-design problem, and we're looking forward to doing that. And we're looking to sort of strike that right balance of, there are going to be lots of places where we keep doing terabytes per TCO, and others where we want IOPS per TCO, and looking at sort of where that makes sense in a variety of different applications, both on-prem and in the cloud. So delighted to have spent this time with you and look forward to continued discussion. Thank you so much for your partnership.